The DevOps Playbook, Strategies for Agile, Efficient, and Reliable Software Delivery. Chapter 1, The DevOps Revolution, Understanding the Core Principles. Imagine a time not so long ago when constructing a new piece of software felt like building a complex bridge by two entirely separate teams, working in complete isolation. On one side, the developers were the architects and structural engineers, meticulously designing and constructing the bridge's components. They were focused on innovation, new features, and the elegance of their designs. On the other side were the operations engineers, who were responsible for the very ground the bridge stood on, the materials used, and ensuring it could withstand the forces of nature. Their focus was stability, reliability, and keeping the existing infrastructure sound. The problem arose when these two teams, despite their individual brilliance, tried to connect their work. The developers would throw their completed bridge sections over a metaphorical wall to the operations team, who would then discover incompatibilities with the existing infrastructure, unforeseen stresses, or simply a lack of understanding about how the new sections were meant to integrate. This often led to delays, finger-pointing, and a general sense of frustration. Software releases were infrequent, unpredictable, and often riddled with problems. This was the reality of traditional IT. In today's hyper-connected world, this approach is no longer viable. Businesses now live or die by their ability to innovate rapidly, deliver seamless digital experiences, and adapt to lightning-fast market changes. The demand for speed, reliability, and uncompromising security in software delivery has never been higher. This pressing need led to a revolution, not just in how software is built, but in how people work together to build and deliver it. This revolution is what we call DevOps. What is DevOps? Defining the philosophy. At its heart, DevOps is not a tool, a job title, or a department you can simply buy. It is a cultural and professional movement that advocates for better collaboration and communication between development and operations teams, aiming to automate and integrate the processes required to build, test, and release software more rapidly, reliably, and frequently. Think of it as dismantling that metaphorical wall and replacing it with a shared construction site, where developers and operations engineers work side by side from the very inception of an idea, through its development, testing, deployment, and ongoing operation. They share tools, goals, and most importantly, responsibility. This philosophy is deeply influenced by earlier movements like Agile software development, which emphasized iterative development, customer collaboration, and responding to change over following a rigid plan. DevOps extends Agile principles beyond the code, applying them to the entire software delivery pipeline, right up to the point where the software is running effectively in the hands of the end user. It also draws heavily from lean manufacturing principles, focusing on eliminating waste, optimizing flow, and continuously improving the value stream. A powerful way to understand DevOps is through the 3 Ways model popularized by Gene Kim in the Phoenix Project and the DevOps Handbook. The first way, flow or systems thinking. This focuses on optimizing the end-to-end delivery of value to the customer. It means looking at the entire software value stream, from idea to production, and identifying bottlenecks and impediments. The goal is to maximize the speed and quality of work flowing through the software development and delivery process. This includes using practices like continuous integration and continuous delivery. The second way, feedback. This emphasizes creating clear, rapid, and constant feedback loops throughout the entire value stream. When a problem occurs, information about it must flow quickly and effectively to those who can fix it, and crucially, to those who can prevent similar problems in the future. This includes monitoring systems, logging, and practices like blameless postmortems for learning from failures. The third way, continuous learning and experimentation. This fosters a culture of continuous experimentation and learning from both successes and failures. It recognizes that mastery requires practice and that every improvement is an opportunity to learn more. This includes practices like chaos engineering, structured experimentation, and sharing knowledge across teams. These 3 ways form a holistic approach that guides both the cultural and technical transformations inherent in DevOps. Key pillars of DevOps. While the three ways provide the foundational philosophy, the practical application of DevOps rests on several key pillars. Culture. As we discussed, this is paramount. It's about fostering collaboration, shared responsibility, empathy, and trust between all teams involved in the software lifecycle. It's moving from "it's not my job" to "we're all in this together." Automation. Automating repetitive, manual tasks across the entire pipeline, from code integration and testing to infrastructure provisioning and deployment. This reduces human error, increases speed, and ensures consistency. Lean practices. Applying lean manufacturing principles to the software delivery process. This means identifying and eliminating waste, reducing batch sizes, making smaller changes more frequently, and striving for continuous improvement. Measurement. What gets measured gets managed. This pillar emphasizes the importance of collecting data on every aspect of the delivery pipeline: deployment frequency, lead time for changes, mean time to recovery, and change failure rate. These metrics provide objective insights for informed decision-making and continuous improvement. Sharing. Encouraging the sharing of knowledge, tools, and best practices across teams. This includes documentation, internal forums, and cross-functional training to build a collective intelligence that benefits the entire organization. Benefits of adopting DevOps. The shift to DevOps isn't just about making engineers happier, though it often does. It delivers tangible, significant business value across the board. Faster time to market. By streamlining processes and automating tasks, organizations can deliver new features and bug fixes to users much more quickly. This means quicker realization of business value. Increased deployment frequency and reliability. DevOps enables teams to deploy changes not annually or quarterly, but daily, hourly, or even continuously. Paradoxically, smaller, more frequent deployments are less risky and more reliable than large, infrequent ones. Reduced lead time for changes. The time it takes for an idea or a code change to go from conception to production is dramatically shortened, allowing organizations to respond rapidly to market demands and customer feedback. Improved system stability and resilience. Through practices like infrastructure as code, automated testing, and comprehensive monitoring, systems become more stable, easier to recover from failures, and more resilient to unexpected events. Better collaboration and employee satisfaction. Breaking down silos and promoting shared goals reduces friction, boosts morale, and creates a more positive, productive work environment for both development and operations teams. Enhanced security. By embedding security practices throughout the entire development lifecycle, DevSecOps, vulnerabilities are identified and remediated much earlier, making systems inherently more secure. Consider the dramatic transformation of companies like Netflix. In their early days, they faced challenges typical of traditional IT, with monolithic applications and infrequent releases. As they scaled and embraced DevOps principles, particularly moving to a microservices architecture and cloud-native operations with heavy automation, they achieved the ability to ship software hundreds, even thousands, of times a day. This agility wasn't just a technical achievement. It directly fueled their capacity for relentless innovation, personalized user experiences, and rapid market dominance in the streaming industry. While a large-scale example, the underlying principles apply to organizations of all sizes. Common misconceptions to avoid. Before we dive deeper, it's essential to clarify what DevOps is not. DevOps is not a product you can buy. You can't purchase a DevOps solution off the shelf. While tools are crucial enablers, DevOps is primarily about people, processes, and culture. It's just about tools. While automation tools are integral, they are merely instruments to achieve cultural and process goals. Without the right mindset and collaborative spirit, simply adopting tools will not deliver true DevOps benefits. It's only for large tech companies. DevOps principles are scalable and adaptable for organizations of any size, from small startups to large enterprises across various industries. The benefits of speed, reliability, and collaboration are universal. Conclusion: the DevOps revolution is fundamentally reshaping how organizations deliver software. It's a move from rigid, siloed processes to flexible, collaborative, and highly automated workflows. It's about bridging the historical divide between development and operations to foster a culture of shared responsibility, continuous feedback, and relentless improvement. While the journey can be challenging, the rewards, faster innovation, superior quality, and a more empowered workforce are well worth the effort. In the chapters that follow, we will break down the essential components of a robust DevOps practice, starting with the most critical element, the culture. We'll explore how to cultivate the right mindset, integrate key technical practices like continuous integration and delivery, automate your infrastructure, ensure robust security, measure your progress, and stay ahead in this ever-evolving landscape. Key takeaways: DevOps is a cultural and technical transformation aimed at improving collaboration, automation, and overall software delivery efficiency. It extends Agile and Lean principles to the entire software delivery lifecycle, from development through operations. The three ways, flow, feedback, and continuous learning experimentation, provide a philosophical framework for understanding DevOps. Key pillars include culture, automation, lean practices, measurement, and sharing. Adopting DevOps leads to significant business benefits, including faster time to market, increased reliability, and enhanced security. DevOps is a philosophy and a journey, not a product or a one-time implementation. Chapter 2: Cultivating a DevOps Culture, People, Collaboration, and Mindset. In the previous chapter, we established that DevOps is far more than just a collection of tools or technologies. It is fundamentally a cultural and philosophical shift. While automation, tooling, and processes are undeniably crucial enablers, culture is the bedrock upon which successful DevOps implementations are built. Without a supportive, collaborative, and learning-oriented culture, even the most sophisticated tools will fall short. As the saying goes, culture eats strategy for breakfast. In DevOps, it eats tools for lunch too. This chapter delves into the people aspect of DevOps, how teams can transform their interactions, mindsets, and responsibilities to truly embrace the principles of continuous delivery and operational excellence. Breaking down silos, the you build it, you run it philosophy. Historically, the software development lifecycle was often a sequential handoff process. Developers would write code, then toss it over to a quality assurance (QA) team for testing, and finally, after much back and forth, hand it off to operations for deployment and maintenance. This created distinct organizational silos: Dev built and Ops ran. This separation of concerns often led to friction. Developers, focused on delivering new features rapidly, might not fully understand the operational complexities or stability requirements. Operations, focused on system stability, might view new deployments from dev as inherent risks to uptime. No one truly owned the full lifecycle from idea to impact. The you build it, you run it philosophy, famously pioneered by Amazon, shatters these silos. It means that the same team that writes the code is also responsible for its operation, performance, and reliability in production. This doesn't mean developers become full-time system administrators, but rather that they gain a direct, first-hand understanding of their software's behavior in the real world. This shared ownership brings immense benefits: empathy and shared responsibility. Developers gain empathy for operational challenges, e.g., service outages, performance bottlenecks, and operations teams understand the pressure to deliver new features. This fosters shared ownership for the software's success from inception to end of life. Faster, more informed feedback. When the team that builds also runs, they directly experience the consequences of their choices. Poorly performing code or difficult-to-monitor services lead to immediate, painful feedback, encouraging better practices. Reduced blame. With shared responsibility, the adversarial dev versus ops dynamic dissolves. Instead of blaming each other, teams collaborate to solve problems and improve processes. Key cultural attributes. A healthy DevOps culture is characterized by several key attributes that permeate daily interactions and decision-making. Collaboration and communication. This is foundational. Teams must actively communicate, not just at formal meetings, but continuously and informally. This involves common chat channels, shared dashboards, joint problem-solving sessions, and a willingness to understand each other's perspectives. It's about building bridges between individuals and departments. Shared responsibility and empathy. Every individual and team understands they are part of a larger value stream. They care about the success of the overall product and the end-user experience, not just their specific part of the code or infrastructure. Empathy allows developers to appreciate operational constraints and operations, to understand development pressures. Trust and transparency. Teams must trust each other to do their best work, make mistakes, and learn from them. Transparency means openly sharing information metrics, incidents, challenges, and successes. When data is hidden or manipulated, mistrust builds. Psychological safety. The belief that one won't be punished or humiliated for speaking up with ideas, questions, concerns, or mistakes is crucial here. Blame-free postmortems or retrospectives. When incidents occur, and they will, the focus should be on what happened and how to prevent it from happening again, not who caused it. A truly blame-free postmortem encourages honesty, deep analysis of systemic issues, and collective learning. This is a powerful feedback loop for continuous improvement. Companies like Google are famous for their extensive use of blameless postmortems. Continuous learning and improvement. The technology landscape is constantly evolving. A DevOps culture embraces this by encouraging experimentation, skill development, and knowledge sharing. Teams seek feedback, learn from failures, and constantly look for ways to optimize their processes and systems. This is directly tied to the third way of DevOps: customer centricity. Ultimately, everything done in DevOps should trace back to delivering value to the customer. This shared external focus helps align disparate teams and provides a common purpose. Organizational structures for DevOps. While you build it, you run it. Agile promotes smaller, cross-functional teams. Larger organizations often adopt hybrid models to support this philosophy. Cross-functional product teams. These are the core units, ideally composed of developers, QA, operations specialists, and sometimes product owners or designers. They own a specific product or service end-to-end, from development through production. Enabling teams. These teams provide expertise and support to the product teams, helping them adopt new technologies, tooling, or practices. They don't do the work for the product teams, but enable them to do the work more effectively. Platform teams. For larger organizations, a platform team provides shared services and infrastructure, e.g., CI/CD pipelines, common logging monitoring platforms, standardized cloud infrastructure that product teams can consume. This prevents each product team from reinventing the wheel and ensures consistency. The key is to avoid simply rebranding your existing ops team as DevOps and creating a new silo. True DevOps strives to break down the wall, not just repaint it. Leadership's role in cultural transformation. Cultural change cannot be mandated. It must be cultivated, and leadership plays a pivotal role. Leaders must lead by example, demonstrate collaborative behavior, champion transparency, and participate in blame-free discussions. Communicate the why. Explain the strategic importance of DevOps to the entire organization, connecting it to business goals and customer value. Provide resources and remove impediments. Ensure teams have the time, training, and tools necessary for the transition. Actively remove organizational blockers. Empower teams. Trust teams to make decisions, experiment, and learn. Avoid micromanaging the how. Recognize and reward desired behaviors. Celebrate cross-team collaboration, successful automation efforts, and effective learning from incidents. Practical steps for fostering culture. So, how can an organization begin to cultivate this desired culture? Joint training and workshops. Send developers and operations staff to the same training courses. Organize internal workshops where they can learn about each other's roles, challenges, and tools. Shared metrics and incentives. Align metrics across dev and ops that reflect end-to-end success, e.g., customer satisfaction, lead time for changes, system uptime. Avoid individual or team-specific incentives that create conflicting goals. Cross-pollination and rotations. Encourage operations engineers to spend time embedded within development teams and vice versa. Even short rotations or shadowing experiences can build immense empathy and understanding. Internal DevOps days or tech talks. Regularly scheduled sessions where teams can share their experiences, showcase successful automations, or discuss recent production incidents in a blame-free way. Brown bag lunches. Informal sessions where engineers from different departments can share knowledge, tools, and challenges over lunch. A large financial institution, grappling with slow software delivery and frequent production issues, decided to tackle their cultural divide head-on. They started with a small, critical project. Instead of separate dev and ops teams, they created a single, co-located product team that included developers, a QA specialist, and an operations engineer. This team was given full ownership, from coding to deployment and monitoring. The immediate challenges were miscommunication and differing priorities. However, through daily stand-ups where everyone shared their work and challenges, joint problem-solving sessions, and mandatory blame-free postmortems for every small issue, they slowly built trust. The developers began writing more operationally friendly code, and the operations engineer started providing input on architectural decisions for better deployability. Within 6 months, their deployment frequency for that product increased by 500%, and their incident rate dropped significantly. The success of this pilot became a powerful example, inspiring other teams to adopt similar collaborative structures. Challenges and overcoming resistance. Cultural change is almost never easy. You will encounter resistance to change. People are comfortable with existing routines and may fear losing control or relevance in a new model. Transparency, clear communication of the why, and involving people in the change process are crucial. Lack of skills or understanding. Individuals may lack the necessary technical skills, e.g., developers needing operational knowledge or ops needing coding skills. Invest heavily in training and provide opportunities for skill development. Management buy-in. Without consistent support from senior leadership, cultural initiatives will falter. Continually demonstrate the business value of DevOps through metrics and success stories. Conclusion: DevOps places people at its center. While automation provides the speed and efficiency, it is the fundamental shift in how people interact, communicate, and take responsibility that truly defines a successful DevOps journey. Building a culture of collaboration, transparency, shared ownership, and continuous learning is not a checkbox to be ticked. It's an ongoing commitment, the bedrock upon which the entire DevOps edifice rests. In the absence of a strong culture, even the most advanced tools and processes will struggle to deliver their full potential. Key takeaways: culture is the most critical component of DevOps success. Automation and tools are merely enablers. Breaking down dev and ops silos through shared ownership, often characterized by the "you build it, you run it" philosophy, is essential. Key cultural attributes include collaboration, empathy, trust, transparency, blame-free learning from failures, and continuous improvement. Organizational structures like cross-functional product teams, enabling teams, and platform teams support a DevOps culture. Leadership plays a vital role in championing and supporting cultural transformation. Fostering a DevOps culture requires practical steps like joint training, shared metrics, and cross-pollination to build empathy and shared understanding. Chapter 3: Continuous Integration (CI), Building a Solid Foundation. In the previous chapter, we explored the critical role of culture in enabling a successful DevOps practice, emphasizing collaboration and shared ownership. Now, we shift our focus to the concrete technical practices that underpin rapid and reliable software delivery. The first, and arguably most fundamental of these, is continuous integration, CI. Think of software development as building a large, intricate Lego model. If each team member works on their own separate piece for weeks on end and only tries to combine them at the very last minute, the chances are high that the pieces won't fit, or there will be significant rework required. This integration hell is a common nightmare in traditional software development. Continuous integration is the practice of avoiding this nightmare by adopting the mantra: integrate early, integrate often. It's the disciplined approach of frequently merging code changes from all developers into a central, shared repository, and then automatically verifying these changes through an automated build and test process. This ensures that new code works seamlessly with the existing codebase, and that any regressions or conflicts are detected immediately. What is continuous integration? At its core, continuous integration means frequent integration. Developers commit their code changes to a shared version control system, like Git, multiple times a day or at least daily. This contrasts sharply with long-lived feature branches that might only be merged after weeks or months. Automated verification. Every time code is integrated, it automatically triggers a build process. This typically involves compiling the code, if it's a compiled language, running automated tests, especially unit and component tests, and performing static code analysis. Rapid feedback. If the build or any of the automated tests fail, the team is notified immediately. This fast feedback loop allows developers to pinpoint and fix issues while the changes are fresh in their minds, dramatically reducing the time and effort required for debugging. The goal is to maintain a consistently working mainline of code. If a problem is introduced, it's caught within minutes, not days or weeks, when it's much harder and more expensive to resolve. Core practices for effective CI. To implement robust CI, several key practices are essential. Version control everything. The absolute foundation of CI is a robust version control system. While many exist, Git has become the industry standard due to its distributed nature and powerful branching capabilities. Not just application code, but also configuration files, infrastructure definitions, and automated tests should be stored in version control. Branching strategies. While feature branches are common, in a CI context, the emphasis is often on short-lived feature branches that are merged back into the main development line very quickly, e.g., within hours or a day. Some teams even adopt trunk-based development, where all developers commit directly to the main branch, often relying on feature toggles to hide unfinished features. This promotes continuous integration and reduces merge conflicts. Automated builds. The process of compiling source code into an executable application must be fully automated and repeatable. This includes resolving dependencies, packaging the application, and preparing it for deployment. Manual build processes introduce errors and inconsistencies. Automated testing, unit and component. With every code integration, a suite of automated tests must run. Unit tests are fast, isolated tests that verify small units of code, e.g., a single function or method. Component tests check the functionality of individual components in isolation. These tests provide the first line of defense against regressions and ensure that new code doesn't break existing functionality. Single source of truth. The central version control repository should be the definitive source for all code. Developers should pull the latest version frequently and push their changes back just as often. Fast feedback loops. The CI system must be configured to provide immediate notifications when a build fails or tests don't pass. This might involve chat messages, email alerts, or prominently displayed dashboards, e.g., a build radiator screen in the team area to make the failure highly visible. The team's collective responsibility is to fix a broken build immediately. Build artifact management. Once a successful build occurs, the resulting deployable package, the artifact, should be stored in a dedicated artifact repository. This ensures that the exact same build that passed all tests is the one deployed, preventing discrepancies. Code quality checks. Static analysis tools can automatically inspect code for style violations, potential bugs, security vulnerabilities at an early stage, and code complexity. Integrating these checks into the CI pipeline helps enforce coding standards and improve overall code health. CI pipeline components, conceptual. While specific tools vary, a conceptual CI pipeline typically involves these elements: source code management, SCM, where all your code lives, e.g., Git repository. CI server service, the orchestrator that monitors the SCM for changes, triggers builds, runs tests, and manages the pipeline, e.g., Jenkins, GitLab CI/CD, GitHub Actions, CircleCI, Azure DevOps. Build tools, used to compile, package, and sometimes run local tests specific to your chosen programming language or framework, e.g., Maven, Gradle, NPM, Netcore CLI. Test runners. Execute your automated unit, component, and sometimes integration tests, e.g., JUnit, NUnit, Jest. Artifact repository, a central storage for all successfully built and tested deployable artifacts, e.g., Nexus Artifactory. Benefits of strong CI. Implementing CI as a core practice yields numerous advantages. Early detection of defects, the most significant benefit. Problems are caught early when they are small, localized, and much easier and cheaper to fix. Reduced integration risks. Frequent integration virtually eliminates the integration hell of merging large, disparate codebases, making the process smoother and less prone to conflicts. Higher code quality. Automated tests and static analysis enforce quality gates, leading to a more stable and maintainable codebase. Confident and predictable releases. When your mainline is always in a working state and you have quick feedback loops, you can be much more confident about the stability of your releases. Improved developer productivity. Developers spend less time debugging complex integration issues and more time writing new features. The confidence gained from fast feedback empowers them. Consider a software team that was struggling with weekly releases. Each release cycle involved days of frantic debugging, with developers pointing fingers at each other's code whenever a new bug appeared. Merging code was a painful experience, often leading to merge conflicts that took hours to resolve. They decided to adopt continuous integration. They implemented a simple CI server, enforced daily commits to the main branch, and built a comprehensive suite of automated unit and component tests that ran with every commit. Initially, it was challenging. Builds broke frequently. However, the team made it a rule: the build must be green. They quickly learned to make smaller, more focused commits and to fix any build failures immediately. Within 2 months, their release cycles became almost boringly predictable. Bugs were rare in releases because they were caught within minutes of being introduced, and merge conflicts became a distant memory. This newfound stability allowed them to increase their release frequency to multiple times a week. Practical tips for implementation. Start small, don't try to automate everything at once. Pick one small project or a critical module to implement CI for first. Don't break the build, make it a cultural commitment. If someone breaks the build, it's their top priority to fix it immediately. This shared responsibility reinforces the you build it, you run it mentality. Keep builds fast. If your CI build takes too long, e.g., more than 10 to 15 minutes, developers will be tempted to bypass it or ignore failures. Focus on optimizing build times through efficient testing strategies and powerful build infrastructure. Invest in comprehensive unit tests. Unit tests are the fastest and cheapest tests to run. A high percentage of code coverage by unit tests forms a strong safety net for frequent integrations. Conclusion: continuous integration is not merely a technical practice. It's a cornerstone of the DevOps philosophy, embodying both the flow and feedback aspects of the 3 ways. By committing to frequent integrations, automated verification, and rapid feedback, teams build a solid foundation of code quality and stability. This stable foundation is what enables the next crucial step in the DevOps journey: the ability to continuously deliver and deploy software with confidence. Key takeaways. Continuous integration, CI, involves frequent merging of code changes into a central repository, followed by automated builds and tests. Its primary goal is to detect and fix integration issues and regressions early, dramatically reducing their cost and impact. Core practices include robust version control, fully automated builds, comprehensive automated unit and component testing, and rapid feedback loops. CI leads to earlier bug detection, reduced integration risk, higher code quality, and improved developer confidence and productivity. A strong CI practice is the essential prerequisite for achieving continuous delivery and deployment. Chapter 4. Continuous delivery, CD, and deployment, automating the release pipeline. With a solid continuous integration, CI, practice in place, our software is now frequently integrated, automatically built, and continually tested to ensure a healthy code base. This provides us with a high degree of confidence that our application logic is sound. However, a working application on a developer's machine or a CI server is not yet delivering value to end users. This is where continuous delivery, CD, and continuous deployment, CD, come into play, extending the automation and feedback loops beyond just code integration to the entire release process. Imagine building a complex machine on an assembly line. CI ensures each component is perfectly manufactured and tested before it leaves its workstation. Continuous delivery and deployment are like the rest of that assembly line. Assembling the components, conducting final quality checks, packaging the machine, and efficiently delivering it to the customer. What are continuous delivery, CD, and continuous deployment? While often used interchangeably, there's a subtle yet crucial distinction between continuous delivery and continuous deployment. Continuous delivery, CD. This practice means that your software is always in a deployable state. Every change that passes automated CI tests is automatically packaged, tested further, e.g., integration, system, performance tests, and then made available in an environment from which it could be deployed to production at any time. The decision to actually push to production remains a manual one, often triggered by a business decision, a scheduled release, or a human approval step. The emphasis is on readiness for deployment, not necessarily immediate deployment. Continuous deployment, CD. This takes continuous delivery a step further. In continuous deployment, every change that passes all automated tests is automatically deployed to production without any human intervention. The only reason a change might not go to production is if it fails any of the automated stages in the pipeline. This is the ultimate expression of automation and trust in your pipeline. When to choose each approach? Most organizations start with continuous delivery. It provides immense benefits by ensuring a deployable artifact is always ready, reducing release anxiety. Continuous deployment is often the aspiration, and it is suitable for mature teams with very high levels of automation, testing, monitoring, and confidence in their pipeline. It requires tremendous trust in the automated checks to be the sole gatekeepers to production. The deployment pipeline, conceptual. The deployment pipeline is the automated sequence of stages. A software change goes through from commit to production. It's the technical manifestation of the flow principle in the 3 ways of DevOps. A typical conceptual pipeline might look like this. Stage 1, commit stage, CI. Covered in Chapter 3, code committed, unit tests, static analysis, build. If successful, creates a deployable artifact. Stage 2, acceptance integration testing. The freshly built artifact is deployed to a dedicated testing environment, often mirroring production. Automated integration tests, API tests, and end-to-end functional tests run here. Stage 3, performance load testing. The application's behavior under stress is measured. Stage 4, staging user acceptance testing, UAT, a pre-production environment ideally identical to production. Here, business stakeholders or QA might perform final manual checks, exploratory testing, or user acceptance testing on the exact build that will go live. This stage often has a manual gate for approval. Stage 5, production deployment. The application is deployed to live users. This stage also triggers post-deployment checks and monitoring. Each stage acts as a gate, and if any test or check fails, the pipeline is stopped and the team is immediately notified, preventing faulty code from progressing further. Core practices for effective CD/CD. To build a robust and reliable continuous delivery deployment pipeline, several practices are fundamental. Automated end-to-end testing. Beyond unit tests, CD relies heavily on a comprehensive suite of automated tests that cover the system from end to end. This includes integration tests, verifying interaction between different modules or services, functional tests, ensuring the system meets specified requirements, performance and load tests, assessing how the system behaves under anticipated and peak loads, security tests, as discussed in DevSecOps Chapter 7, Infrastructure as Code, ISC. This is paramount for CD. Consistent environments are critical. If your staging environment behaves differently from production because it was manually configured, your testing loses its value. ISC ensures that environments are identical, repeatable, and version-controlled, more detail in Chapter 5. Configuration management. Managing application configurations, e.g., database connection strings, feature flag settings, consistently across different environments is crucial for reliable deployments. Configuration should be externalized from the code and managed dynamically for each environment. Deployment strategies. To minimize risk during production deployments, various advanced strategies are employed. Blue-green deployments, maintaining two identical production environments, blue and green. While blue is live, the new version is deployed to green and thoroughly tested. Traffic is then switched from blue to green. Quick rollback by switching traffic back. Canary releases, deploying the new version to a small subset of users, the canary group, to test it in a live environment. If stable, gradually roll out to more users. Feature flags or feature toggles, allowing new features to be deployed to production in a disabled state, and then selectively enabling them for specific users or all users without a new deployment. This decouples deployment from release. Rolling deployments, iteratively updating instances of an application in a cluster, taking down a few, updating them, bringing them back up, and moving to the next set. Automated rollback mechanisms, the ability to quickly and reliably revert to a previous, stable version of the application if an issue is detected post-deployment. This provides a crucial safety net and reduces the stress associated with deployments. Small, frequent releases. Small changes are easier to understand, test, and troubleshoot. They also reduce the blast radius if something goes wrong. The goal is to make deployments boring and routine. Security scanning in pipeline, integrating deeper security checks, e.g., dynamic analysis, dependency vulnerability scanning, into later stages of the CD pipeline ensures comprehensive security coverage. Benefits of CD/CD. The advantages of implementing continuous delivery and deployment are transformative for any organization. Faster time to market. New features and bug fixes reach users much faster, allowing businesses to adapt quickly to market demands and gain a competitive edge. Reduced risk per deployment. Smaller, more frequent deployments reduce the scope of change, making it easier to identify and fix issues. Automated testing and rollback capabilities further mitigate risk. Faster feedback from users. Getting new features into users' hands quickly allows for rapid, valuable feedback, which can then inform the next iteration of development. Improved system reliability. Consistent processes, automated testing, and reliable deployment strategies lead to more stable and performant systems. Reduced stress and manual errors. Automating the deployment process eliminates the fraught, error-prone manual steps traditionally associated with releases, leading to happier, less stressed teams. Consider a retail banking application, traditionally deploying updates once every quarter. Due to the infrequency, each release was a massive event, a big bang, that required weekend downtime, war rooms, and extensive manual checks. The risk was enormous, and errors were common. After embracing CD, they built an automated pipeline using ISE to provision identical environments and developed a robust automated test suite. They began using blue-green deployments for their customer-facing web application. Now, they could deploy updates weekly, sometimes even daily. When a critical security patch was needed, it could go live within hours, not weeks. The Big Bang was replaced by a series of small, low-risk, routine updates, drastically improving their agility and reducing operational stress. Practical tips for implementation. Start with CD before contemplating continuous deployment. Get comfortable with the idea that your software is always deployable. Automating the human decision to go live is the final, often most challenging, step. Automate everything in the pipeline. Any manual gate or step becomes a bottleneck and a source of potential error. Strive for full automation. Make deployments boring and routine. The ideal deployment is so routine that no one even notices it's happening. This is achieved through automation, small changes, and robust safety nets. Invest heavily in automated testing. Your CD pipeline is only as reliable as your automated tests. Flaky or insufficient tests will undermine confidence and prevent you from moving towards full automation. Conclusion: continuous delivery and continuous deployment are the powerful engines that drive rapid, reliable software releases in the DevOps world. By extending automation beyond code integration to the entire release pipeline, teams can deliver value to users with unprecedented speed and confidence. These practices embody the flow principle, minimizing friction and maximizing the pace at which ideas become customer value. With CI providing the foundation of code quality and CD/CD ensuring its efficient journey to production, we are now ready to delve into how to manage the environments upon which this software runs. Key takeaways. Continuous delivery ensures software is always in a deployable state. Continuous deployment automates the release to production entirely. The deployment pipeline orchestrates the journey of code from commit to production through automated stages and gates. Essential practices include comprehensive automated testing, infrastructure as code for consistent environments, and smart deployment strategies like blue-green or canary releases. CD/CD leads to faster time to market, reduced risk, rapid feedback, and improved system reliability. Automate every possible step in the pipeline to make deployments routine and low stress. Chapter 5. Infrastructure as Code, ISC and Automation. Managing environments at scale. In the journey towards continuous delivery, we discovered how crucial it is to have consistent and reliable environments for testing and deployment. If your tests run perfectly in a development environment, but fail in a staging environment because of subtle configuration differences, then your highly automated pipeline becomes fragile. This is precisely where Infrastructure as Code, ISC, steps in, fundamentally changing how we manage and provision our computing environments. Traditionally, provisioning servers, configuring networks, and setting up databases were manual, often laborious, and error-prone processes. An operations engineer would log into machines, click through interfaces, or run scripts by hand. This led to Snowflake servers' unique, manually configured environments that were difficult to reproduce, troubleshoot, and scale. Imagine trying to consistently bake a cake if each time you used slightly different ingredients and oven temperatures. The results would be unpredictable. Infrastructure as Code transforms this ad hoc approach into a repeatable, automated, and version-controlled practice. What is Infrastructure as Code, ISC? At its core, ISC is the practice of managing and provisioning computer data centers through machine-readable definition files, rather than physical hardware configuration or interactive configuration tools. Simply put, you describe your infrastructure using code, just like you would describe an application. Instead of manually clicking to set up a server, you write a text file that declares what kind of server you need, what software should be installed on it, and how it should be networked. This code is then executed by a tool that interprets your declarations and provisions the infrastructure precisely as specified. This means treating infrastructure definitions with the same rigor and practices as application code. Version control. Infrastructure definitions are stored in a version control system, like Git, allowing you to track changes, revert to previous versions, and collaborate. Code reviews. Just like application code, infrastructure code can be reviewed by peers for errors, security vulnerabilities, or inefficiencies before being deployed. Testing. Infrastructure configurations can be tested automatically, ensuring that they will behave as expected before they are applied to live systems. Core principles of ISC. Several key principles guide effective ISC implementations. Declarative versus imperative. Declarative ISC, desired state. You describe the desired end state of your infrastructure. The tool figures out the steps to get there. For example, you might declare, I need a web server with Apache installed and running. The ISC tool will determine if Apache is installed, install it if not, and ensure it's running. This is generally preferred for its simplicity and robustness. Imperative ISC, step-by-step instructions. You provide step-by-step instructions on how to achieve a state. For example, first, create a virtual machine. Then install operating system X, then install Apache. Then start Apache. While providing granular control, imperative scripts can be harder to manage and less resilient to unforeseen conditions. Idempotency, a crucial characteristic of ISC tools. An idempotent operation is one that, when executed multiple times, yields the same result as executing it once. This means if you run your ISC script after a component has already been provisioned, It won't break anything or create duplicates. It will simply ensure the component matches the desired state. This allows for safe, repeated application of configurations. Immutability. This principle promotes treating servers and infrastructure components as immutable objects. Instead of updating or patching an existing server, you create a new, updated server from scratch and replace the old one. This ensures consistency and prevents configuration drift over time. Version control. As mentioned, storing all ISC files in a version control system is non-negotiable. It provides a historical record, enables collaboration, and allows for quick rollbacks if an infrastructure change introduces problems. Testing infrastructure. Just as you test application code, you should test your infrastructure code. This can involve linting, checking for syntax errors, validating configurations, and even deploying to temporary environments to test functionality. Why ISC is a DevOps best practice. ISC is not just a nice-to-have. It is fundamental to achieving high-performing DevOps practices. Consistency eliminates the snowflake server problem. Every environment, development, testing, staging, and production can be provisioned identically from the same code. Ensuring that it works on my machine actually means it works everywhere. Repeatability. Need a new environment for a temporary project or to scale up? ISC allows you to spin up new, identical environments quickly and reliably. Speed. Manual provisioning can take hours or days. With ISC, complex infrastructures can be deployed in minutes. This dramatically accelerates the entire software delivery pipeline. Reduced errors. By automating the provisioning and configuration process, human error is significantly reduced, leading to more stable and reliable systems. Cost efficiency. ISC enables efficient resource utilization. Environments can be spun up only when needed, e.g., for testing, and then torn down, reducing infrastructure costs, particularly in cloud environments. It also supports auto-scaling efficiently. Security and compliance. Security policies, network configurations, and access controls can all be defined in code, ensuring they are consistently applied and auditable. Compliance adherence becomes a built-in feature rather than an afterthought. Types of ISC, conceptual. While various tools exist, ISC broadly encompasses provisioning tools, used to create the foundational infrastructure components like virtual machines, containers, networks, load balancers, and databases, e.g., cloud provider APIs, Terraform conceptually. Configuration management tools, used to install and manage software within those provisioned components, set up user accounts, manage services, and ensure desired configurations are maintained, e.g., Ansible, Puppet, Chef, SaltStack conceptually. Orchestration tools, used to manage and coordinate groups of services, particularly in containerized environments, ensuring applications are running, scaled correctly, and interconnected, e.g., Kubernetes conceptually. Many modern solutions blur these lines, offering capabilities across multiple categories. The key is understanding their purpose rather than memorizing a long list of specific product names. Consider a large software company with hundreds of development teams, each requiring multiple environments, development, testing, integration for their various projects. Developers constantly complained, "It works on my machine, but not on the test server." The operations team struggled to keep all environments consistent and up to date. By adopting ISC, they moved to a model where every environment was defined by version-controlled code. When a developer needed a new test environment, they simply ran a command, and an identical, pristine environment was spun up in minutes. This not only eliminated the "works on my machine" problem, but also freed up the operations team from tedious manual setup, allowing them to focus on building more robust and automated platforms. Practical considerations for ISC adoption. Gradual adoption. You don't have to automate all your infrastructure overnight. Start with new projects or specific components, learn, and then expand. Standardization. While ISC provides flexibility, establishing standards for how environments are defined and managed can significantly simplify maintenance and collaboration. Security practices for ISC. Just like application code, ISC files contain sensitive information and define critical system access. Treat them with extreme care, apply least privilege principles, and regularly audit for vulnerabilities. Integrating ISC into CI/CD pipelines. Once your infrastructure is defined as code, the next logical step is to treat it like application code. This means integrating ISC changes into your CI/CD pipeline, running automated tests against them, and automatically applying them to environments. Challenges. While the benefits are clear, implementing ISC can present challenges. Learning curve. Adopting new tools and paradigms requires engineers to learn new skills. Managing complexity. As infrastructure grows, ISC definitions can become complex. Proper structuring, modularization, and good hygiene are essential. Legacy systems integration. Integrating ISC with existing, manually provisioned legacy systems can be difficult and may require significant migration efforts. Conclusion. Infrastructure as code is a cornerstone of modern software delivery, moving infrastructure management from an artisanal craft to an engineering discipline. By treating infrastructure definitions as code and subjecting them to the same rigorous practices as application code, organizations unlock unprecedented levels of speed, consistency, reliability, and cost efficiency. It enables the creation of truly ephemeral environments, where infrastructure can be spun up, used, and torn down on demand, becoming a seamless extension of the automated CI/CD pipeline. With our infrastructure now defined, provisioned, and managed through code, the next crucial step is to understand and monitor the behavior of our systems once they are live, ensuring they deliver the expected value. Key takeaways. Infrastructure as code, ISC, defines and provisions infrastructure using machine-readable code, treating it like application code. Key principles include declarative definitions, idempotency, immutability, version control, and testing. ISC is essential for DevOps because it ensures consistency, repeatability, speed, reduced errors, cost efficiency, and improved security compliance of environments. It supports faster and more reliable continuous delivery by providing consistent target environments. While powerful, successful ISC adoption requires careful planning, skill development, and integration into existing workflows. Chapter 6, Observability. Monitoring, logging, and tracing for insights. We've explored how DevOps helps us build, test, and deliver software with incredible speed and reliability. But what happens once that software is live and serving users? How do we know if it's performing as expected? How do we quickly identify and resolve issues when they inevitably arise? This brings us to the critical practice of observability. In the past, operations teams often relied solely on monitoring, setting up alerts to tell them if a server was up or down, if CPU usage spiked, or if a database was reachable. While important, this is like a pilot only knowing if the plane's engines are on or off. To truly understand the state of a complex system, especially modern distributed architectures like microservices, you need more than just a binary status check. You need the ability to ask arbitrary questions about its internal state, even for issues you didn't anticipate. This is the essence of observability. Monitoring versus observability. A crucial distinction. While often used synonymously, understanding the difference between monitoring and observability is key. Monitoring. The practice of collecting predefined data points, metrics, from systems and applications to understand their health and performance for known conditions. Monitoring answers questions like, is the CPU overloaded? Are there too many errors? Or is the service available? It tells you if something is wrong or already broken based on what you've pre-configured to look for. It's about knowing known unknowns. Observability. The ability to understand the internal state of a system by examining its external outputs. It allows you to debug unknown unknowns, problems you didn't anticipate and haven't pre-configured alerts for. Observability answers questions like, why is the API endpoint suddenly slower? What caused this specific customer's transaction to fail? Or, which specific microservice is introducing latency in this request chain? It's about having enough rich data to ask any question about system behavior and get a meaningful answer. In essence, monitoring tells you what is or potentially is wrong. Observability helps you figure out why it's wrong, how it happened, and what's connected to it. It's like the difference between a car with a check engine light monitoring and a car with a detailed diagnostic system that tells you precisely which sensor is failing and its impact on performance. Observability. The 3 pillars of observability. To achieve true observability, systems typically rely on 3 fundamental signal types. Metrics, numerical values representing a system's behavior over time. These are aggregated, quantifiable measurements, suitable for trending, alerting, and dashboarding. Examples: CPU utilization, memory usage, network traffic, requests per second, error rates, latency, response time, queue depth. Best practice: define service level indicators, SLIs, to measure predefined quality targets, and then set service level objectives, SLOs, around acceptable performance. Alerts should be configured based on these SLOs. Where it fits. Metrics are excellent for detecting trends and anomalies, e.g., error rate just spiked by 50%. Logs, time-stamped records of discrete events that occur within an application or system. Logs provide detailed, granular information about what happened at a specific point in time. Examples: user login attempt, database query execution, function call, error messages, warning messages. Best practice: centralize logs from all services and infrastructure into a single platform. Implement structured logging, e.g., JSON format, to make them easily parsable and searchable. Ensure logs contain sufficient context, e.g., trace IDs, request IDs, user IDs, to aid debugging. Where it fits. Logs are crucial for understanding what happened leading up to an event, e.g., the error happened after this sequence of interactions. Traces represent the complete lifecycle of a single request or transaction as it propagates through different services and components in a distributed system. A trace shows the sequence of events and time taken at each step. Examples: a user request moving from a load balancer through an API gateway to a microservice, then making calls to a database and another microservice, and finally returning a response. Best practice: implement distributed tracing across all services. Each service should propagate a unique trace ID and span IDs for each operation it performs. Where it fits. Traces are invaluable for understanding why a particular request was slow or failed in a complex distributed architecture, pinpointing bottlenecks or erroneous service interactions. These 3 pillars are symbiotic. They offer different perspectives on system behavior. Metrics tell you there's a problem, logs help you understand the specific context of the problem, and traces show you the full journey that led to it. Correlating data across these 3 pillars provides the most powerful insights. Implementing observability as a best practice. Instrumenting applications. Observability starts at the code level. Developers must instrument their applications to emit the right metrics, logs, and traces. This isn't an afterthought. It's part of designing a production-ready application. Centralized aggregation. Collect all metrics, logs, and traces from every part of your infrastructure and applications into centralized platforms. This enables correlation, powerful searching, and comprehensive visualization. Visualization and alerting. Present the collected data in intuitive dashboards tailored to different roles: developers, operations, product managers. Configure intelligent alerts that notify the right teams about critical issues before they impact customers significantly. Avoid alert fatigue by making alerts actionable and meaningful. Feedback loops. Observability data shouldn't just be for post-mortem analysis. It should power continuous improvement, the 3rd way of DevOps. Use insights from observability to inform development decisions, optimize performance, and refine architecture. Contextual information. Always ensure that data points are enriched with relevant context, e.g., environment, service name, version, user ID, request ID. This makes debugging far more efficient. Benefits of strong observability. Faster mean time to recovery, MTTR. By quickly pinpointing the root cause of issues, teams can resolve incidents significantly faster, minimizing downtime and business impact. Proactive issue detection. Early warning signs from metrics and intelligent alerts can help teams address problems before they escalate into major outages. Improved understanding of system performance and user experience. Observability provides objective data on how systems are performing and how users are experiencing the application, leading to better product and infrastructure decisions. Informed decision-making. Data-driven insights from observability tools help teams prioritize work, identify bottlenecks, allocate resources, and assess the impact of changes. Better debugging in complex, distributed systems. Tracing, in particular, is indispensable for unraveling the intricate interactions within microservices architectures, making debugging manageable. Consider a popular e-commerce platform that was suffering from intermittent checkout page slowdowns, especially during peak traffic. Their traditional monitoring told them that their web servers were high on CPU and memory, but it couldn't tell them why or where the bottleneck truly was. By implementing distributed tracing and structured logging, they gained visibility into the entire checkout process. They discovered that a particular API call to a third-party payment gateway was occasionally taking 5 to 10 seconds, and that their own recommendation engine microservice, while fast on its own, was making too many redundant queries. With this specific, actionable data, they were able to optimize their payment gateway integration and refactor the recommendation engine, eliminating the slowdowns. This wasn't possible with just high-level capacity monitoring. It required deep observability into the flow of requests. Practical tips. Start with basic metrics and logs. Even simple CPU, memory, network metrics, and centralized application logs can provide significant value. Build up your observability practice incrementally. Standardize logging formats. Agree on a common format, e.g., JSON, for all your application logs. This makes parsing, searching, and analyzing logs across different services much easier. Define clear SLIs and SLOs. Work with product owners to define what constitutes acceptable performance and reliability for your services. This helps focus observability efforts on what truly matters. Practice observability-driven development. Encourage developers to consider how their code will be observed in production while they are writing it. This leads to better instrumentation from the start. Challenges. Data volume and cost. Observability can generate vast amounts of data, which can be expensive to store and process. Smart sampling and data retention policies are necessary. Complexity of instrumentation. Instrumenting every part of a complex system can be challenging and requires careful planning. Alert fatigue. Too many alerts, or alerts that are not actionable, can lead teams to ignore them entirely. Focus on meaningful alerts based on SLO violations. Conclusion. Observability is the eyes and ears of your production systems in the DevOps world. It's the essential practice that allows teams to understand, debug, and ultimately improve the reliability and performance of their software in live environments. By meticulously collecting and analyzing metrics, logs, and traces, organizations can move from reactive firefighting to proactive system mastery, ensuring their valuable software continues to run smoothly and deliver exceptional user experiences. With our systems now observable, our next step is to ensure they are also inherently secure throughout their lifecycle. Key takeaways. Observability is the ability to understand internal system state from external outputs, crucial for debugging unknown unknowns. It goes beyond simple monitoring, which focuses on known unknowns and predefined metrics. The 3 pillars of observability are metrics, quantifiable measurements, logs, event records, and traces, end-to-end request flows. Effective observability leads to faster mean time to recovery, MTTR, proactive issue detection, better system understanding, and informed decision-making. Implementation requires instrumenting applications, centralized data aggregation, effective visualization and alerting, and using data for continuous improvement. Chapter 7, DevSecOps, integrating security throughout the lifecycle. We've seen how DevOps empowers rapid delivery, fosters collaboration, and ensures system reliability. But in an increasingly interconnected and threat-laden digital landscape, there's a vital missing piece if security isn't intrinsically woven into every stage: DevSecOps. Historically, security was often treated as a gate at the very end of the software development lifecycle, a final audit before deployment. Development teams would build features, operations would deploy them, and only then would security teams perform scans or penetration tests. When vulnerabilities were found, it often meant costly, time-consuming rework, delaying releases and fostering friction between teams. This security-last approach is no longer sustainable. With the speed of modern DevOps pipelines, waiting until the end is akin to installing seatbelts after a car has crashed. DevSecOps is the practice of integrating security considerations and tooling into every phase of the development and operations pipeline, from initial design and coding, shifting left, through testing, deployment, and continuous monitoring in production, shifting right. It represents a fundamental cultural shift where everyone involved in the software delivery process takes shared responsibility for security. What is DevSecOps? DevSecOps is essentially DevOps with security embedded. It champions the idea of security as code and introduces automated security checks, policy enforcement, and proactive security measures at every possible opportunity within the CI/CD pipeline. The core tenets of DevSecOps are: shift left, integrate security as early as possible in the software development lifecycle. The earlier a vulnerability is caught, the cheaper and easier it is to fix. Security as a shared responsibility. Security is not solely the domain of the dedicated security team. Developers, operations engineers, and QA personnel all share accountability for building and maintaining secure systems. Automation. Automate security testing, policy enforcement, and vulnerability management within the CI/CD pipeline to maintain speed while improving security posture. Continuous improvement. Regularly review, assess, and update security practices based on feedback, new threats, and lessons learned. Why integrate security? The imperative for DevSecOps is clear: cost of fixing vulnerabilities. The cost of identifying and remediating a security vulnerability increases exponentially the later it is found in the lifecycle. Fixing a bug found in production can be 100 times more expensive than one found during coding. Compliance and regulatory requirements. Many industries face stringent regulatory requirements, e.g., GDPR, HIPAA, PCI DSS. DevSecOps helps embed compliance by design, making audits smoother and continuous compliance more achievable. Protecting brand reputation and customer trust. Data breaches and security incidents can severely damage a company's reputation and erode customer trust, leading to significant financial losses and long-term consequences. Increasing attack surface. Modern architectures, cloud, microservices, APIs, increase complexity and expand the potential attack surface. Security must keep pace with this evolution. Key DevSecOps practices. Integrating security throughout the pipeline involves a range of practices. Security by design and threat modeling. Early in the lifecycle, security considerations begin during the design and architecture phases. Threat modeling. Systematically identifying potential threats and vulnerabilities to applications and infrastructure from a malicious actor's perspective. This informs design choices and security controls. Security in development, shift left. Secure coding practices, training developers in writing secure code. Static application security testing, SAST. Automated tools analyze source code, bytecode, or binary code to detect security vulnerabilities, e.g., SQL injection, cross-site scripting, before the application is run. This integrates into the CI stage. Software composition analysis, SCA. Automated tools scan for vulnerabilities in open-source libraries and third-party dependencies used in the application. Given the prevalence of open-source components, this is critical. Security unit testing. Writing tests that specifically target security requirements or known vulnerabilities. Security in CI/CD pipeline automation. Dynamic application security testing, DAST. Automated tools test the application in a running state, simulating attacks to find vulnerabilities that might not be visible in static code, e.g., API issues, runtime configuration flaws. This typically occurs in testing or staging environments. Container security scanning. scanning container images for known vulnerabilities before deployment. Secrets management, securely storing and managing sensitive information like API keys, database credentials, and certificates, preventing them from being hard-coded or exposed. Tools for secret management ensure they are injected securely at runtime. Infrastructure as code, ISC security scanners, tools that analyze your ISC templates, e.g., Terraform, CloudFormation, for security misconfigurations and compliance violations before infrastructure is provisioned. Automated policy enforcement, implementing rules and policies directly within the pipeline, e.g., no unencrypted S3 buckets, only approved container images. Security in operations, shift right/continuous monitoring. Runtime application self-protection, RASP, security technology that's integrated into the application runtime, constantly monitoring its behavior for attacks and actively blocking them. Vulnerability management, continuous scanning of production environments for vulnerabilities and misconfigurations. Security information and event management, SIEM, centralized collection and analysis of security logs from applications, infrastructure, and security devices to detect threats and facilitate incident response. Incident response automation, automating responses to security incidents, such as isolating compromised systems. Security chaos engineering, proactively injecting security failures or misconfigurations to test the resilience of the system and the effectiveness of security controls and incident response procedures. Tooling landscape conceptual. This involves categories of tools for SAST, DAST, SCA, container scanners, secret managers, vulnerability scanners, SIEM, etc. The specific tools chosen will depend on the technology stack and organizational needs. Building a secure pipeline. The ideal DevSecOps pipeline weaves these practices seamlessly into the existing CI/CD flow. Code commit triggers SAST, SCA, and security unit tests. Build artifact. Container image scanning. Deploy to test staging. Trigger DAST, ISC security scanning, and potentially compliance checks. Produce reports. Security findings are fed back to development teams, ideally within their familiar tool chain, e.g., IDE integration, pull request comments. Production, continuous monitoring, vulnerability management, and incident response. Practical tips for implementation. Start small. Don't try to implement every security control at once. Prioritize critical vulnerabilities and start automating security checks for those. Even simple linting and dependency scanning can provide huge value. Automate wherever possible. Manual security checks quickly become bottlenecks in a fast-paced DevOps environment. Automate repetitive tasks to maintain velocity. Foster collaboration, the most critical aspect. Facilitate regular communication, joint training, and shared goals between security teams, developers, and operations engineers. Security personnel should be embedded within development teams, acting as enablers rather than just auditors. Provide continuous security education. Developers are often not security experts. Provide regular training on secure coding practices, common vulnerabilities, and new threats. Treat security issues like bugs. Integrate security findings directly into the development team's issue tracking system, prioritizing them based on severity. A global software company, historically struggling with recurring SQL injection vulnerabilities in their web applications, had a breakthrough when they embraced DevSecOps. They implemented a SAST tool directly into their CI pipeline, configured to run on every code commit. Initially, developers were overwhelmed by the number of findings. However, a small team of security and development leads collaborated to tune the SAST tool, create secure coding guidelines, and deliver focused training sessions. They also introduced an SCA tool to automatically flag vulnerable open-source libraries. Within 6 months, the number of SQL injection vulnerabilities caught before reaching production dropped by 95%, and the time to fix the remaining ones decreased significantly. This transformed security from a reactive bottleneck to a proactive accelerator. Challenges: lack of security expertise in DevOps. Developers and operations engineers often lack deep security knowledge. Bridging this skill gap requires significant investment in training. Alert fatigue. Security tools can generate a high volume of alerts, many of which may be false positives or low severity. Tuning tools and prioritizing alerts is crucial. Balancing speed with security. It can be challenging to integrate security measures without slowing down the development and deployment process. Automation is the key to maintaining velocity. Legacy applications. Integrating DevSecOps practices with older, monolithic applications might be more complex than with new, cloud-native ones. Conclusion: DevSecOps is not an option. It's a necessity in the modern digital landscape. By embedding security into every phase of the software delivery lifecycle, organizations can build more robust, resilient, and trustworthy systems. It transcends the traditional security gate by empowering every team member to be a guardian of security, making it an integral part of the continuous value stream. With security woven in, the final piece of the quality puzzle is ensuring that our applications function correctly and perform well under real-world conditions. Which brings us to the crucial role of testing in DevOps. Key takeaways: DevSecOps integrates security practices into every stage of the DevOps pipeline, shifting security left and making it a shared responsibility. It provides significant benefits by reducing the cost of vulnerability remediation, ensuring compliance, and protecting brand reputation. Core practices include threat modeling, SAST, SCA, DAST, container scanning, secrets management, ISC security scanning, and continuous monitoring. Automation is key to maintaining speed while integrating security. Successful DevSecOps requires significant collaboration, education, and a cultural shift where everyone owns security. Chapter 8: Testing in DevOps. Ensuring quality at speed. We've explored how DevOps helps us deliver software with speed, CI/CD, consistency, ISC, and resilience, observability, DevSecOps. But what about quality? How do we ensure that rapid delivery doesn't lead to a flood of bugs and a decline in user experience? This brings us to the critical role of testing in DevOps, which undergoes a significant transformation from traditional QA practices. In classic software development, quality assurance, QA teams often functioned as gatekeepers at the end of the development cycle. They would receive a completed feature, manually test it, and then declare it production-ready or send it back for rework. This approach created bottlenecks, slowed down releases, and often left major bugs undiscovered until late in the process, when they were most expensive to fix. In DevOps, the paradigm shifts dramatically. Quality is no longer the sole responsibility of the QA team. It becomes everyone's responsibility. Testing is not a phase that happens after development, but an activity that happens continuously and throughout the entire lifecycle. The mantra is test early, test often, automate everything. The paradigm shift in testing for DevOps. The core changes in testing for a DevOps environment are: from end-of-lifecycle testing to continuous testing. Rather than a big bang of testing at the end, testing is integrated into every stage of the CI/CD pipeline, providing rapid feedback. From manual to automated testing. Manual testing, while still having its place, e.g., exploratory testing, cannot keep pace with frequent deployments. Automation is paramount. From QA as gatekeepers to quality enablers, QA professionals evolve from solely finding bugs to educating developers on testing best practices, building test frameworks, and helping automate quality gates. Quality is everyone's responsibility. Developers implement unit and integration tests. Operations teams ensure systems are testable and provide data for performance testing. Security teams integrate security tests. The test automation pyramid. A widely used conceptual model for structuring automated testing is the test automation pyramid, popularized by Mike Cohn. It dictates the relative proportion of different types of tests an organization should aim for. Unit tests, base of the pyramid. Focus. Testing the smallest individual units or components of code, e.g., a single function, method, or class in isolation. Characteristics. Fast to execute, inexpensive to write and maintain, provide immediate feedback to developers. Quantity should be the largest number of tests in your automation suite. They form the bedrock of your quality assurance. Integration tests, middle layer. Focus, verifying the interactions between different units or components or between your code and external dependencies, databases, APIs, file systems. Characteristics, slower than unit tests but still relatively fast. They detect issues that arise when components communicate. Quantity, fewer than unit tests but still a substantial number. Service API tests, middle layer, typically above integration tests. Focus, testing the public interfaces of a service or application, e.g., REST APIs, message queues, without requiring a full graphical user interface. This is crucial for microservices architectures. Characteristics, faster and more stable than UI tests, allowing broad coverage of backend logic. UI/end-to-end tests, top of the pyramid. Focus, simulating user interaction with the complete system through its graphical user interface. Characteristics, slowest to execute, most expensive to write and maintain, and often the most flaky, prone to breaking due to minor UI changes. Quantity should be the smallest number of tests. Only use them for critical user journeys and scenarios that cannot be covered by lower-level tests. The idea is to maximize coverage at the lowest, fastest level of the pyramid to get rapid feedback, reserving slower, more expensive tests for broader system interactions and user flows. Types of automated tests in the pipeline. Beyond the pyramid, other essential types of automated testing in DevOps include performance testing, load, stress, scalability. Simulating high user traffic to assess how the system behaves under anticipated and peak loads. This includes measuring response times, throughput, and resource utilization. Security testing, covered in Chapter 7, DevSecOps, includes SAST, DAST, SCA, etc., integrated into the pipeline. Chaos engineering, proactively injecting failures, e.g., latency, service outages, resource exhaustion, into a running system to test its resilience and verify that it handles unexpected events gracefully. Accessibility testing, ensuring the application is usable by people with disabilities. Regression testing, automatically rerunning existing tests to ensure that new changes haven't introduced unintended side effects or broken previously working functionality. Best practices for automated testing. Test early, test often. Integrate automated tests into your CI/CD pipeline from the very first commit. The quicker you get feedback on changes, the less costly it is to fix issues. Fast and reliable tests. Tests must execute quickly and consistently. Flaky tests, those that sometimes pass and sometimes fail without code changes, erode trust in the pipeline. Prioritize making tests deterministic and stable. Treat tests as first-class citizens. Store test code in version control alongside application code. Apply the same code quality standards, code reviews, and maintenance efforts to your test suite. Test data management. Automated tests often require specific test data. Implement strategies for generating, managing, and cleaning up test data to ensure test isolation and repeatability. Test environment management. Leverage infrastructure as code, ISE, to create consistent, isolated, and automatically provisioned test environments. This ensures tests run against a known, predictable setup. Shift-right testing, testing in production. While shift-left focuses on early detection, shift-right embraces the reality that some issues only manifest in live production environments. This includes practices like feature flags toggles, deploying new features in a disabled state and enabling them gradually for specific user segments. Canary releases, releasing a new version to a small subset of production users. A/B testing, simultaneously running two versions of a feature to compare performance or user behavior. Real user monitoring, RUM, tools that collect data on user experience directly from end users' browsers or devices. Synthetic monitoring, automated scripts that simulate user interactions 24/7. Test-driven development, TDD, /behavior-driven development, BDD. These methodologies encourage writing tests before writing the code they are meant to test, greatly improving test coverage and code design. Consider a development team that, initially, outsourced all their QA to a separate department. Releases were slow, and quality was inconsistent. They decided to embrace a whole-team approach to quality, Developers were trained in TDD and unit testing. The QA professionals transformed into quality coaches, helping the development team build robust automated test suites for integration and API layers. They adopted a strategy where every pull request had to pass all automated unit and integration tests before it could even be considered for merge. For UI tests, they focused on only the most critical end-to-end user journeys. The outcome was remarkable. Not only did their deployment frequency dramatically increase, but the number of critical production defects plummeted by 80%, leading to higher customer satisfaction and increased team morale. Challenges: writing and maintaining good tests. Crafting effective, non-flaky automated tests requires skill and discipline. Flaky tests that occasionally fail for no apparent reason, are a major source of frustration and erode trust in the pipeline. Eliminating flakiness is crucial. Performance overhead. Comprehensive testing adds execution time to the pipeline. Optimizing test execution, e.g., parallelization, and strategically choosing test types is vital. Coverage versus effectiveness. Aiming for 100% code coverage can lead to writing worthless tests. Focus on tests that provide meaningful value and cover critical paths. Conclusion: testing in DevOps is a continuous, automated, and collaborative activity that ensures rapid delivery doesn't compromise quality. By leveraging the test automation pyramid, integrating comprehensive testing into every stage of the CI/CD pipeline, and fostering a culture where quality is everyone's responsibility, organizations can build confidence in their releases and consistently deliver high-quality software at speed. With our pipelines automated and our quality assured, the next logical step is to understand how we measure the impact of these changes and drive continuous improvement. Key takeaways: quality is everyone's responsibility in DevOps. Testing is continuous and integrated throughout the lifecycle. The test automation pyramid provides a strategy for balancing different test types, prioritizing faster, lower-level tests. Key automated tests include unit, integration, API, UI, performance, security, and chaos engineering. Best practices include testing early and often, treating tests as first-class citizens, managing test data environments, and embracing shift-right testing in production. Effective testing within DevOps enables faster feedback, increased confidence in releases, and reduced defects. Chapter 9: Measuring DevOps Success. Metrics, KPIs, and continuous improvement. We've covered the cultural shifts, the automation of continuous integration and delivery, the power of infrastructure as code, the insights provided by observability, the integration of security, and the necessity of pervasive testing. All these practices are meant to transform how software is built and delivered, ultimately aiming for better business outcomes. But how do we know if our efforts are actually succeeding? How do we demonstrate the value of DevOps? The answer lies in measurement. As the management guru Peter Drucker famously said, "What gets measured gets managed." In DevOps, this adage is particularly apt. Without clear, actionable metrics, it's impossible to truly understand the effectiveness of your processes, identify bottlenecks, celebrate successes, or justify further investment. Metrics provide the objective data needed for continuous improvement, forming the crucial feedback loop that closes the DevOps cycle. Why measure DevOps? The reasons for measuring your DevOps journey are multifaceted and compelling. Demonstrate business value. Translate technical improvements into tangible business benefits, e.g., increased revenue, reduced operational costs, higher customer satisfaction. Identify bottlenecks and areas for improvement. Pinpoint where processes are slow, where quality issues arise, or where teams are struggling. Metrics reveal the pain points. Encourage continuous learning and experimentation. Data from experiments, new processes, tools proves whether changes lead to desired outcomes, informing future decisions. Align teams around shared goals. When dev, ops, security, and other teams share common metrics for success, it fosters a unified approach and reduces siloed thinking. Support data-driven decision-making. Move away from opinion-based discussions to objective, evidence-based improvements. Key DevOps metrics, the DORA metrics. One of the most impactful frameworks for measuring DevOps performance comes from the DevOps Research and Assessment (DORA) team, now part of Google Cloud. Their extensive research, published in the State of DevOps report, has identified 4 key metrics that strongly correlate with organizational performance and are excellent predictors of successful software delivery. Deployment frequency. Definition: how often an organization successfully releases changes to production. What it indicates: the ability to release software quickly and frequently. High deployment frequency is generally a sign of a highly automated, low-risk release process. Relation to the 3 ways directly relates to the flow and feedback principles. Small, frequent deployments imply smooth flow and rapid feedback. Goal: more is better. Elite performers deploy multiple times a day. Lead time for changes. Definition: the time it takes for a commit to get into production. Often measured from code committed to code running in production. What it indicates: the overall efficiency of your development and delivery pipeline. It encompasses development, testing, deployment, and approval processes. Relation to the 3 ways directly relates to flow. A shorter lead time means a quicker path from idea to value. Goal: shorter is better. Elite performers have lead times typically under an hour. Mean time to restore, MTTR. Definition: how long it takes to restore service after an outage or incident. What it indicates: the effectiveness of your incident response, monitoring, and recovery processes. It's a measure of resilience. Relation to the 3 ways directly relates to feedback and continuous learning. Fast recovery implies strong feedback loops and the ability to diagnose issues quickly. Goal: shorter is better. Elite performers achieve recovery in less than an hour. Change failure rate. Definition: the percentage of changes to production that result in degraded service, outages, or require rework rollback. What it indicates: the quality and stability of your changes and the robustness of your testing and deployment processes. Relation to the 3 ways directly relates to feedback and continuous learning. A low change failure rate shows effective testing and a culture of learning from mistakes. Goal: lower is better. Elite performers have a change failure rate typically below 15%. These 4 metrics provide a holistic view of software delivery performance, encompassing both speed and stability. They are the North Star for continuous improvement in DevOps. Other important metrics. While the DORA metrics are paramount, other metrics can provide valuable granular insights depending on your context. Customer satisfaction. Surveys, Net Promoter Score, NPS, or direct feedback related to system uptime, performance, and new features. Ultimately, this is what DevOps aims to improve. Cost of delivery operations. Unit cost of infrastructure, cost per deployment, optimization of cloud spend FinOps. Number of incident severity, detailed breakdown of production issues. Throughput metrics. Number of stories features delivered, average cycle time of a feature. Code quality metrics, technical debt, test coverage, code complexity, number of security vulnerabilities. Team satisfaction burnout. Employee engagement surveys. Healthy teams are more productive and innovative. Setting up a measurement strategy. Define clear goals. What business outcomes are you trying to achieve? How do these align with your DevOps practices? Identify relevant metrics. Based on your goals, choose the DORA metrics and any other supporting metrics that provide actionable insights. Automate data collection. Manually collecting metrics is tedious and error-prone. Leverage your CI/CD tools, monitoring systems, and project management tools to automatically capture data. Visualize data, dashboards. Present metrics clearly and visually using dashboards that are accessible to all relevant stakeholders. Trends are often more important than single data points. Establish baselines and targets. Understand your current performance and set realistic, aspirational targets for improvement. Using metrics for continuous improvement. Metrics are not just for reporting, they are for action and learning, making them a key aspect of the 3rd way of DevOps. Identifying bottlenecks. A high lead time for changes might indicate a slow manual approval process, inadequate testing automation, or a cumbersome deployment step. Conducting retrospectives. Use the DORA metrics and other data points in your team's regular retrospectives to discuss what went well, what didn't go well, And what can we improve based on objective evidence? Example: our change failure rate increased last sprint. Let's drill into the incidents and understand why. A/B testing and experimentation. Use metrics to evaluate the impact of new features or process changes. Sharing insights. Regularly communicate performance metrics across teams and to leadership. Celebrate improvements and openly discuss challenges. An organization embarked on a DevOps transformation. For years, their software releases were once a month, often involving all-nighters and last-minute bug fixes. Their lead time for changes was weeks, and their change failure rate was routinely 30 to 40%. They started by diligently tracking the DORA metrics. Initially, the numbers were grim, but they provided a clear, undeniable picture of their pain points. They used this data to justify investments in better automated testing, reducing change failure rate, streamlining their approval processes, reducing lead time, and implementing blue-green deployments, increasing deployment frequency and reducing MTTR. Over 18 months, their lead time dropped from weeks to days, change failure rate plummeted to under 10%, and deployment frequency increased to several times a week. These improvements, supported by hard data, not only proved the value of their DevOps efforts, but also made the development team happier and more productive. Common pitfalls in measurement. Vanity metrics. Metrics that look good but don't provide actionable insights or directly relate to business value, e.g., lines of code written. Measuring individuals instead of team systems. Blaming specific individuals based on metrics can destroy psychological safety and collaboration. Focus on system and team performance. Too many metrics, analysis paralysis. Overloading teams with too many metrics can lead to distraction and overwhelm. Focus on a few key, actionable indicators. Ignoring the why behind the numbers. Metrics tell you what is happening, but not always why. Always combine quantitative data with qualitative analysis, e.g., root cause analysis, team discussions. Not acting on the data. Collecting metrics without using them to drive improvements is a wasted effort. Conclusion: metrics are the compass for your DevOps journey. By systematically measuring performance through key indicators like the DORA metrics, organizations gain invaluable insights into their software delivery capabilities. These insights fuel continuous learning and experimentation, identify areas for investment and improvement, and ultimately demonstrate the profound impact of DevOps on business outcomes. With a robust measurement strategy in place, you are not just adopting DevOps practices, you are intelligently steering your organization towards sustained excellence. Key takeaways. Measurement is crucial for understanding the effectiveness of DevOps, identifying bottlenecks, and driving continuous improvement. The DORA metrics, deployment frequency, lead time for changes, MTTR, change failure rate, are powerful indicators of software delivery performance and predict organizational success. Metrics should be automated, visualized, and used actively to inform data-driven decisions and retrospectives. Avoid common pitfalls like vanity metrics, measuring individuals, analysis paralysis, and failing to act on the data. Chapter 10, The Future of DevOps, Emerging Trends and Staying Ahead. We have journeyed through the core principles and practices of DevOps, from cultivating a collaborative culture to automating the entire software delivery pipeline, securing systems, ensuring quality, and measuring success. We've established that DevOps is not a static destination, but a continuous journey of improvement and adaptation. In this final chapter, we look to the horizon, exploring the evolving landscape of DevOps and discussing how to remain resilient and relevant in a world of constant technological change. DevOps is a philosophy built on adaptability. As technology evolves and business demands shift, so too do the practices and focus areas within the DevOps community. Staying at the forefront requires continuous learning, experimentation, and an open mind. Evolving concepts and trends. Several key trends and emerging concepts are shaping the future of DevOps. Platform engineering. As organizations scale their DevOps adoption, they often face a common bottleneck: individual product teams having to build and maintain their own CI/CD pipelines, observability stacks, and infrastructure components. This leads to duplication of effort and inconsistency. Platform engineering addresses this by creating managed, self-service platforms that provide common tools, services, and guardrails for product teams. Think of it as building a robust internal product that enables product teams to deliver value faster and more efficiently, abstracting away underlying infrastructure complexities. It's like providing paved roads and readily available vehicle types, rather than asking every team to build their own roads and cars from scratch. FinOps. With widespread adoption of cloud computing, managing cloud spend effectively has become critical. FinOps brings financial accountability to the variable spend model of the cloud, enabling organizations to make business trade-offs between speed, cost, and quality. It's a cultural practice that unites finance, technology, and business teams to drive financial accountability for cloud costs. DevOps principles of collaboration and continuous improvement are essential here, as engineering teams need visibility into costs and the tools to optimize resource usage. Site reliability engineering, SRE. While DevOps is a cultural and operational philosophy, SRE, championed by Google, is often described as what happens when you ask a software engineer to design an operations function. SRE emphasizes using software engineering principles to automate operations and manage system reliability at scale. SRE teams often define service-level objectives, SLOs, and service-level indicators, SLIs, manage error budgets, and promote practices like chaos engineering. While distinct, SRE and DevOps are highly complementary and often converge in practice, with SRE providing a prescriptive approach to reliability within a DevOps culture. AI ML in DevOps, AIOps. The sheer volume of operational data, logs, metrics, traces generated by modern systems is overwhelming for humans. AIOps leverages artificial intelligence, AI and machine learning, ML techniques to analyze this data, identify patterns, predict issues, correlate events, and even automate remediation. This can lead to faster incident response, proactive problem resolution, and reduced alert fatigue. Examples include intelligent alerting, root cause analysis assistance, and anomaly detection. Cloud-native adoption. The shift towards cloud-native architectures continues to accelerate. This includes widespread adoption of technologies like containers and Kubernetes for packaging, deploying, and managing applications consistently across diverse environments. Serverless computing, abstracting away infrastructure completely, allowing developers to focus solely on code. Service meshes, for managing communication between microservices, handling traffic routing, security, and observability. Advanced cloud-native patterns necessitate sophisticated DevOps practices as they introduce new levels of distribution and complexity. GitOps. Extending infrastructure as code further, GitOps is an operational framework that uses Git as the single source of truth for declarative infrastructure and applications. It defines that all changes to infrastructure or applications in production must be made through Git pull requests. An automated agent then deploys whatever is declared in the Git repository, ensuring observed production state matches the desired state in Git and enabling immediate rollbacks. Supply chain security. As organizations increasingly rely on open-source components and complex build pipelines, securing the entire software supply chain has become a paramount concern. This involves verifying the integrity of all code components, first-party, open-source, third-party, securing build environments, and validating deployment artifacts. This trend intensifies the need for DevSecOps best practices across a wider scope. GreenOps sustainable software, a rapidly emerging trend focusing on minimizing the environmental impact of software and IT infrastructure. This includes optimizing code for energy efficiency, utilizing greener cloud regions, and optimizing resource consumption for computing and storage. DevOps principles can drive these efforts by measuring and optimizing energy usage throughout the software lifecycle. Navigating the future. To thrive in this evolving landscape, individuals and organizations must cultivate certain capabilities. Continuous learning. The pace of change will only accelerate. Staying updated with new tools, technologies, and methodologies is no longer optional. This involves reading, attending conferences, virtual or in person, participating in online communities, and experimenting with new technologies. Experimentation and adaptability. Be willing to try new approaches, embrace failure as a learning opportunity, and adapt your practices based on feedback and results. Don't cling to one tool or process if a better one emerges. Community engagement. Participate in the broader DevOps community. Share your experiences, learn from others' successes and failures, and contribute to open-source projects. Focus on business value. With so many new technologies, it's easy to get lost in the hype. Always anchor your technology choices and process changes back to delivering tangible business value and improving customer experience. The human element endures. Despite the increasing automation and the proliferation of advanced technologies like AI, the human element remains absolutely central to DevOps. AI may analyze logs faster or predict outages, but human creativity, problem-solving skills, and empathy will always be required to address unprecedented challenges, innovate, and make critical decisions. The roles of DevOps professionals will continue to evolve. The lines between developer, operations, and security will further blur. There will be an increased demand for T-shaped, individuals, deep specialists in one area, e.g., security with broad knowledge across the entire software delivery lifecycle. Final thoughts. DevOps began as a response to the pain points of traditional software delivery, aiming to bridge the gap between development and operations. It has grown into a powerful movement that transcends mere tools, representing a fundamental shift in how people collaborate, innovate, and deliver value in the digital age. The journey is never truly over. There will always be new challenges, new technologies, and new opportunities for improvement. By embracing the core principles of culture, automation, lean thinking, measurement, and sharing, and by committing to continuous learning and adaptation, organizations can ensure they remain agile, resilient, and ready to meet the demands of an ever-changing future. May your DevOps journey be one of continuous discovery, collaboration, and success. Key takeaways. DevOps is an evolving philosophy. Staying ahead requires continuous learning and adaptation. Key emergent trends include platform engineering, FinOps, SRE, AI ops, cloud-native adoption containers, serverless, service meshes, GitOps, supply chain security, and GreenOps. Organizations and individuals must foster continuous learning, experimentation, adaptability, and community engagement to navigate these trends effectively. Despite increasing automation, the human element creativity, critical thinking, and collaboration remains central to DevOps success. The future of DevOps is an ongoing commitment to innovation and improvement for sustained excellence in software delivery.